In this step, you'll visualize the synthetic web traffic dataset we saw in previous lessons. Here are the concepts we'll cover. We'll use a library called Matplotlib for plotting utilities. We then make a few plots to explore trends over time. We'll also then tell stories using properly constructed plots. The choice of plot will be intentional to highlight a takeaway we wish to convey. If you've lost your last notebook, or if you're starting the class from this lesson, access a starter notebook for lesson 7 from alvin/data101/notebook 7. Alternatively, you can use your own notebook from the last lesson. Once you access that URL, you should see a page like this one. Go ahead and click on File and save a copy in Drive. This will then create a new copy of the notebook. On this page, I'm going to click on X in the top left to close the navigation bar. Then, regardless of whether you open the new notebook or if you're using your existing notebook, click on Runtime and Run All. Go ahead and then scroll down to the very bottom. Here we're going to start by outputting the correlations we saw before. Go ahead and type in df.core with 2 R's, add your parentheses, and run the cell. Notice 2 things. Video watching appears to be correlated with clicking. So we have video watching and clicking right here at 0.32. Pricing also appears to be weakly correlated with clicking. Here we have 0.10. However, the video can only be watched on Webpage A, and the pricing section can only be read on Webpage B. As a result, it makes more sense to compute correlations for each web page separately. Go ahead and type in viewsa.core. Here are the correlations for Webpage A only. Notice that the correlation between videos and clicking is much higher at 0.67 than we thought. Next, go ahead and compute the correlations for only Webpage B. Type in viewsb.core. And now, run the cell. Here are the correlations for Webpage B. Notice that the correlation between pricing section and clicking is very low. It is much lower than we thought. In fact, we can say that they're not correlated at all. This is close enough to 0. Our first argument for Webpage A, then, is that videos are highly indicative of whether or not the user will register, and reading the pricing section is not. A correlation of 0.67 does not make sense on its own, however. Is this high? Is this low? Is this reasonable? However, a correlation of 0.67 is definitely much higher than a correlation of 0.0004. As a result, we can use a bar plot to emphasize the difference between the two. Start by importing the Matplotlib plotting utility. Type in import matplotlib.pyplot as plt. Now, the first thing we're going to do is call the method title to give your plot a title. Type in plt.title, and you can use whatever text you would like in between these quotes. However, I am going to type in a title of videos are strongly correlated with clicking. I highly suggest adding the main takeaway of your plot in the plot title. Now, we're going to call plt.bar. This will create a bar plot. The first argument for bar is a list of strings, the names of each bar. Here we're going to create a list, and the string is going to be the title. So we'll say page load, we'll say video watching, and the very last bar is going to be correlation with reading the pricing section. Bar also takes in a second list. We're going to pass in the numbers from our correlation table above. Above, our correlation table gives a correlation of negative 0.39 for page load and clicking. It's also a correlation of 0.67 for video watching and clicking. Finally, we have a correlation of 0.0004 between reading the pricing section and clicking. Finally, we need a label for our y-axis. So we're going to say y-label and correlation with clicking. And that's it. This is argument number 1, that videos are highly correlated with signups. Go ahead and run your cell to create your first plot. This is now your bar plot. For our next point, we will need to explore the daily statistics, like the click-through rate over time. To do so, we will need to write a new function to compute daily statistics. Start by defining the function name getDailyStats. So def getDailyStats, and we're going to accept one argument df, and as usual, don't forget your colon. This function will accept one argument called df or the data frame. First thing, we're going to group by day. To do this, we're going to define a grouper. And this is a new variable that is equal to pd.grouper, where the frequency is equal to a day. So here, uppercase D means day. pd.grouper is a generic pandas utility that helps us group rows in a data frame according to some frequency. In this case, our frequency is daily. Next, we're going to define a new variable groups is equal to, and then we're going to call the data frame.groupByGrouper. This is how we can calculate groups of days. Finally, we're going to compute statistics for each group. To do that, we'll type in daily is equal to groups.mean. For each group, take the average of each column. Finally, return the daily statistics. Once you're done with your function, go ahead and run your function. Now we're going to use this function to obtain daily statistics. Go ahead and type in daily views A is equal to get daily statistics, and type in or pass in all of the views for Webpage A. Go ahead and repeat the same thing for the second Webpage B. Type in get daily stats and views of B. To give you an idea of what daily views A contains, we're going to output daily views A. As you may expect, if you run the cell, you'll get a data frame where you now have one row for every single day and the daily statistics for that day, like the average number of video seconds watched, the average page load time, and percentage of viewers that clicked. Now, we'll explore a different kind of plot, a line plot. Go ahead and type in plt.title to give your new plot a title. In this case, our plot title is going to be click-through rates over time. Fortunately, Matplotlib integrates fairly well with pandas. All we need to do is tell Matplotlib which column we want to plot. Go ahead and type in plt.plot and pass in one of the columns from daily views A. In this case, the column is going to be has clicked. Now, we could normally stop here. However, we want to label each of the lines in our line plot. So in this case, go ahead and add a comma and type in label equal to A. This syntax, label equal to A, is not something you've seen before. This is known as a keyword argument. We'll skip over the details of a keyword argument for now. What's important is that this is how you label lines in a line plot. Let's go ahead and now repeat the same thing for Webpage B. Type in plt.plot daily views B and select the column has clicked. Finally, comma and label equals to B, and this labels our second line as B. Next, let's add our legend to the plot. Type in plt.legend, call the function, and that's it. We're now going to add two more lines to label our axes. Type in plt.xlabel, and the x-axis is going to be the dates, and the y-axis is going to be the click-through rate. So go ahead and run the cell, and that's kind of crazy. Look at how much click-through rate for Webpage A, the blue line, drops over time. Wonder what happened? Let's examine some other statistics. So we're going to redo the same code, but this time for page load times. We're going to copy and paste the contents of this cell and then replace parts of it that we'll need to see page load times. Go ahead and copy and paste. We're now going to replace this title with webpage page load times. And then below, we're going to replace the has clicked column with the page load column for both of these. Next, this changes our y-axis. So instead of click-through rate on our y-axis, we now have page load times. In parentheses, I'm going to add the units for this axis. Go ahead and run the cell. And whoa, look at that. Web page time for Webpage A in blue shoots up like mad. So our second argument for Webpage A is that abnormally slow page load times appear to unintentionally damage its click-through rate, suggesting that there is untold potential for Webpage A. To quantify how flawed Webpage A's overall click-through rate is, we can quantify the page load times damage on click-through rate. To do this, we first plot the relationship between click-through rates and page load times. Here, go ahead and type in views of A, page load ds. We're going to create a brand new column which will contain the page load times and their click-through rates for every 20 milliseconds. Go ahead and now type in views of A, page load ms. We're going to floor divide by 20. So a floor divide means that if you have a fraction, you round down to the next integer. Once you've got that, let's go ahead and multiply by 20 again. And what this basically means is that all of your values are in increments of 20. So before, you might have had a value of 34, but now 34 floor divided by 20 will give you 1. And then multiplied by 20 will give you 20. So any value between 20 and 39 will be equal to 20. Any value between 40 up to 59 will become 40, and so on and so forth. This effectively bins all of our page load times into groups of 20 milliseconds. Now, let's go ahead and type in page load is equal to views A dot set index. So this will now change the index. In other words, it'll change the column that we can easily sort or group by. Go ahead and type in page load ds, which is our new column. Then we're going to calculate groups for each binned page load time. Type in page load is equal to views A dot group by page load ds. Make sure to have these square brackets right here. That's actually really important for this function. This will calculate the groups for each binned page load time. Now for each group, we're going to compute the average statistics. So go ahead and type in page load equals to page load dot mean, and that will compute the average statistics for each group. Finally, we want to sort all the data by the binned page load time by calling .sortIndex. This data frame now tells you the average click-through rate for each page load time. Again, if you're overwhelmed by this function or by this cell, that's completely okay. All you need to remember is the general concept of what we've done here. What we did is we first binned all of the values into groups of 20 milliseconds. Then we computed statistics for each of these groups. These two things are perfectly Googleable. So now let's see what this data frame looks like. Type in page load and run the cell. Here, we can now see the statistics for every single one of these 20 millisecond buckets. You can now make a line plot like before by passing in the data frame column. In this case, we care about the click-through rate. So go ahead and type in plt.plot and page load has clicked. And this will plot the page load times impact on the click-through rate. Go ahead and hit run. And now the x-axis is the page load time in milliseconds. The y-axis is the click-through rate. And as you might expect, click-through rate drops as page load time increases. Next, let's fit a line to this to get an approximate number for how quickly click-through rate decreases as page load times increase. Go ahead and import another library called NumPy. This library has a line fitting algorithm that we can use. Go ahead and type in m, b, in other words, the slope and the bias of your line is equal to a NumPy function that will actually fit a line for us to a bunch of points. Call mp.polyfit and pass in the x values, which is all of the page load times. So here you have page load.index, and the second argument is the click-through rate, which is page load and then has clicked. The last argument is the degree of a polynomial. In this case, we want a straight line, so the polynomial of degree 1 is all we need. Now, we can finally summarize the fitted line. Take the slope. Recall that the slope is the rise over run, or alternatively, the change in y over the change in x. Here, y is the click-through rate and x is the page load time. So the slope is the change in click-through rate per change in page load time. We can multiply by 100 to get the change in click-through rate per 100 milliseconds of page load time. Type in m times 100 and go ahead and run the cell. Here we get negative 0.068. This means that every 100 milliseconds slower of page load costs 7% traffic. We're making some pretty sweeping oversimplifications here, but this conveys the point that slower page load times are significantly hurting the click-through rate for Webpage A. I would accompany any presentation that cites a number like this one with a plot to explain. So let's make a plot so that viewers can judge for themselves how well this line fits the data. In the next cell, we'll start off with a title, plt.title. In this case, our title is going to be every 100 milliseconds of page load time costs 7% click-through rate. Plot the line from before in the previous cell one more time. Here, page load has clicked, and the label is the click-through rate. Then plot the fitted line. Here we call pageload.index, and remember the equation for a line is m times x plus b. So here we'll have the m times the x values, just pageload.index plus b. And we're also going to add a label here. The label is going to be the fitted click-through rate. Go ahead and now add a label for your x-axis. This is going to be the page load time in milliseconds. And we're also going to label the y-axis. Here's click-through rate. Finally, add your legend and run your cell. This concludes our second argument. We can now see that the click-through rate is dropping a lot due to increased page load time. Next, we want to understand, for our third argument, what if Webpage A hadn't been impacted by a slower page load time? What do we think Webpage A's click-through rate would have been? Observing the graph above, further up, right here, we notice that Webpage A's page load times all appear to fall within 400 to 550 milliseconds before it appears to jump. As a result, we'll compute the click-through rate for Webpage A using only that data. So we're going to select all views with page load times less than 550 milliseconds. Go ahead and type in views A, and we're going to select all of these columns, all of the page load times that are less than 550. This will give us only the rows that have page load time less than 550 milliseconds. Now let's go ahead and select whether or not that row was clicked on, and then compute the average click-through rate. Go ahead and run the cell. That's a whole 70% click-through rate. Pretty incredible. For comparison, let's compute the click-through rate for Webpage B. Select the click column and again compute the mean. Run this cell, and that gets us just 40% click-through rate. In short, Webpage A would have outstripped Webpage B by a large margin, by 40%. However, to really convey this idea, we'll need a line plot again. In this cell, we'll use the functions we defined earlier to A, get all the click information for each web page. Then B will compute the number of clicks per day for each web page. Go ahead and define a new variable clicks A is equal to, and then get only the click events from all of the views for Webpage A. This only considers clicks for Webpage A. Next, we're going to compute daily statistics. So clicks A daily is equal to, and then events per day, and pass in the variable that we just defined. This computes the number of clicks per day for Webpage A. Go ahead and do the same for Webpage B. Clicks B is equal to all of the click events for Webpage B. And then compute the number of clicks per day for Webpage B. So here, clicks B daily is equal to the events per day of clicks B. In order to see what clicks A daily looks like, go ahead and type that variable name one more time and run the cell. Here we get, for every single day, the number of clicks. Now, our final piece of code in this last cell, we're going to actually plot this data. Type in plt.title to give this plot a title. Webpage A could have boosted CTR by 30%. Go ahead and now plot the data that we just computed, the number of clicks per day. Just like before, we're going to label this line A. Repeat the same for B. So clicks B daily and label equals to B. Next, our third line for this plot is going to be the projected number of clicks for our Webpage A. We're going to multiply the views per day by 0.7. And then we're going to multiply by 0.5 because each web page actually only got half the traffic. Then we're going to type in label equals to A projected, so estimated. This concludes our line. Let's now go ahead and label the axes just like we always do. We're going to label the date, and then we're going to label the clicks. And then add the legend. And finally, that concludes our final plot. Go ahead and run it, and we can see here in the green line that our projected clicks per day for Webpage A would have been insane. It would have been much higher than Webpage B's. So in conclusion, let's go back to the slides. We covered several topics in this lesson: Matplotlib, plot, and how to tell a story. In sum, here are final conclusions. Our initial conclusions had suggested Webpage B was better. Fortunately, we have now corrected that mistake. In summary, we have produced 3 quality figures that support our data-driven business decision. In sum, we recommend picking Webpage A with the informational video. There are 3 reasons. Watching an informational video is strongly correlated with clicking to sign up. By contrast, reading the pricing section has near zero bearing on whether or not the user clicks to sign up. Starting with the top left, we then showed that Webpage A's click-through rate dropped precipitously. In the bottom left, we showed that Webpage A's dropped click-through rate happened at the same time Webpage A's page load times increased suddenly. On the right, we then show that Webpage A's increased page load time resulted in drastic drops in click-through rate. This suggests that Webpage A's overall click-through rate cannot be trusted. Finally, we project what Webpage A's click-through rate would have been throughout the experiment had page load times not shot up 2 months into the experiment. We can see that Webpage A would have consistently sustained 30% higher click-through rate than Webpage B, justifying our final recommendation of Webpage A. And that concludes the data-driven business recommendation. Our final tip: know your plot types. The right plot can tell a story. You should know, for any point that you want to emphasize, which plot is best suited to emphasize that point. Feel free to add additional annotations, change colors, or title the plot appropriately to help. If you'd like to access and download these slides, visit this URL. Try plotting your own data to see if there are hidden insights. If you're looking for the perfect plot type, see Matplotlib examples. The goal is not to collect them all, but your goal is to know what plots will help you tell the right story. Sometimes, browsing that page can give you just enough inspiration. Congratulations! This concludes your first case study of an A/B test for 2 web pages. Next, we'll discuss next steps for you to continue learning more.